Our universe is a vast and awe-inspiring expanse, teeming with celestial objects of unimaginable size and power. From the smallest particles to the largest galaxies, the cosmos is a tapestry of wonders that continues to captivate our imagination and drive our quest for knowledge. Among these cosmic wonders, stars stand out as the most luminous and influential entities, shaping the very fabric of galaxies and giving rise to the conditions necessary for life itself. These celestial beacons have been the subject of human fascination for millennia, guiding explorers and inspiring countless myths and legends. But what exactly are stars, and how do they differ from planets like our own Earth, or the gas giants that roam our solar system? Understanding these differences is key to comprehending the complex dynamics of our universe. Stars are essentially gigantic spheres of plasma, primarily composed of hydrogen and helium, held together by their own immense gravity. These colossal bodies are born in vast clouds of gas and dust known as nebulae, where gravitational forces cause the material to collapse and form a protostar. Unlike planets, which shine by reflecting sunlight, stars possess an internal engine, nuclear fusion, that allows them to generate their own light and heat. This self-sustaining process is what makes stars the brilliant powerhouses of the universe. This process occurs in the star's core, where immense pressure and temperature fuse hydrogen atoms into helium, releasing tremendous amounts of energy in the process. This energy then radiates outward, traveling through the various layers of the star before finally escaping into space as light and heat. Earth, our home planet, is a rocky sphere with a molten core, providing a solid surface for life to thrive. Its unique composition and distance from the sun create the perfect conditions for a diverse range of ecosystems. Gas giants like Jupiter, on the other hand, are colossal planets composed primarily of hydrogen and helium, much like stars. However, their lack of sufficient mass means they cannot initiate the nuclear fusion process. However, unlike stars, gas giants lack the mass and internal pressure to ignite nuclear fusion. They remain as massive spheres of swirling gas with complex atmospheric dynamics and a multitude of moons. They remain as massive spheres of swirling gas, forever bound to orbit their parent stars. These orbits are often accompanied by intricate systems of rings and moons, adding to the complexity and beauty of these giant planets. The distinction between stars and planets lies primarily in their ability to sustain nuclear fusion. This fundamental difference dictates their size, luminosity, and ultimately, their fate in the grand cosmic dance. While stars burn brightly for millions to billions of years, planets remain as silent companions, reflecting the light of their stellar hosts. This fundamental difference dictates their size, luminosity, and ultimately their fate in the grand cosmic dance. Stars, with their fiery cores, will eventually exhaust their nuclear fuel and undergo dramatic transformations, while planets will continue their silent orbits, bearing witness to the ever-changing cosmos around them. In the realm of celestial objects, there exists a fascinating class of objects known as brown dwarfs, often referred to as failed stars. These enigmatic entities blur the line between stars and planets, possessing characteristics of both but ultimately falling short of achieving true stellar status. Brown dwarfs are significantly larger than gas giants like Jupiter, with masses ranging from 13 to 80 times that of our solar system's largest planet. However, they lack the necessary mass to ignite the full-fledged nuclear fusion that powers true stars. Instead, they undergo a limited form of fusion, fusing deuterium, a heavier isotope of hydrogen, for a short period. This deuterium burning phase is short-lived, lasting only a few million years. As the brown dwarf exhausts its limited supply of deuterium, it gradually cools and fades, emitting faint infrared radiation. This lack of sustained nuclear fusion distinguishes brown dwarfs from true stars and relegates them to a state of perpetual cosmic twilight. Despite their failed star status, brown dwarfs remain intriguing objects for astronomers. They offer valuable insights into the processes of star formation and the lower mass limit for stellar ignition. Their study provides a glimpse into the diverse range of objects that populate our universe, highlighting the subtle interplay of mass and gravity in shaping celestial destinies. At the lower end of the stellar mass spectrum lie red dwarfs, the smallest and coolest type of main-sequence stars. These stars, often overlooked due to their faintness, are fascinating in their own right. They are the unsung heroes of the cosmos, quietly burning away in the vast expanse of space. These diminutive dynamos, though often overlooked due to their faintness, represent the most common type of star in the Milky Way galaxy. In fact, red dwarfs make up about 70 to 80% of all the stars in our galaxy, making them the true backbone of the Milky Way. Despite their small size, red dwarfs play a crucial role in the cosmic drama, boasting incredibly long lifespans and potentially harboring planetary systems of their own. Many of these planetary systems are of great interest to astronomers, as they may hold the key to understanding the potential for life beyond our solar system. Red dwarfs are significantly smaller and cooler than our Sun, with masses ranging from about 7.5% to 50% of our star's mass. This size difference is not just a trivial fact, it has profound implications for the star's behavior and lifespan. Their lower mass results in lower core temperatures and pressures, leading to a slower rate of nuclear fusion. This slower fusion process means that red dwarfs burn their fuel much more efficiently than larger stars. This slower burn rate translates to significantly lower luminosity, making red dwarfs much fainter than their more massive counterparts. Their dim light is often lost in the glare of brighter stars, but this does not diminish their importance. One famous example of a red dwarf is Barnard's star, located a mere 6 light-years away from Earth, making it the 4th closest star to our solar system. Barnard's star is a prime example of the quiet, enduring nature of red dwarfs. Despite its proximity, Barnard's star is so faint that it is invisible to the naked eye, highlighting the dim nature of these stellar dwarfs. This faintness is a common trait among red dwarfs, making them challenging to study with traditional telescopes. Despite their faintness, red dwarfs possess incredibly long lifespans, far exceeding that of our Sun. Their longevity is one of their most remarkable features, allowing them to exist for trillions of years. Their slow and steady rate of nuclear fusion allows them to shine for trillions of years, far surpassing the current age of the universe. This means that many red dwarfs that formed early in the universe's history are still burning today. This longevity has sparked considerable interest in the possibility of life evolving on planets orbiting red dwarfs. The extended lifespans of these stars provide a stable environment for potentially habitable planets, giving life ample time to develop and evolve. Scientists are particularly interested in the habitable zones around red dwarfs, where conditions might be just right for liquid water to exist, a key ingredient for life as we know it. Our Sun, the celestial anchor of our solar system, is often perceived as an exceptional and unique star. It is the source of light and warmth, the very essence of life on Earth, and has been a subject of fascination and reverence throughout human history. While it is undeniably special to us, providing the light and heat essential for life on Earth, in the grand scheme of the cosmos, the Sun is classified as a rather ordinary yellow dwarf star. This classification places it among the most common types of stars in our galaxy, the Milky Way. It stands as a middle-aged star, neither exceptionally large nor particularly small, but perfectly suited for its role as the life-giver of our planetary system. The Sun's balanced characteristics make it an ideal candidate for supporting life on the planets that orbit it. With a mass of approximately 1.989 times 10 to the 30th kilograms, the Sun dwarfs all other objects in our solar system combined. This immense mass is what gives the Sun its powerful gravitational pull, which is the force that keeps the planets, asteroids, and comets in their orbits. Its immense gravitational pull governs the orbits of planets, asteroids, and comets, holding our cosmic neighborhood together. Without the Sun's gravitational influence, the planets would drift away into the vastness of space, and our solar system as we know it would cease to exist. The Sun's energy output, primarily in the form of visible light and infrared radiation, bathes our planet in warmth, driving weather patterns, ocean currents, and the very processes that make life possible. This energy is the engine behind the water cycle, photosynthesis in plants, and the climate systems that sustain life on Earth. Compared to red dwarfs, the Sun is a stellar powerhouse. Red dwarfs are smaller, cooler, and much less luminous than our Sun, making them less likely to support life as we know it. Its higher mass and core temperature result in a much faster rate of nuclear fusion, producing a luminosity about 200 times greater than that of a typical red dwarf. This nuclear fusion process converts hydrogen into helium, releasing vast amounts of energy that radiate out into space. This higher energy output translates to a shorter lifespan, with the Sun estimated to have another 5 billion years of life left before it exhausts its nuclear fuel. As it ages, the Sun will undergo dramatic changes, eventually expanding into a red giant, and then shedding its outer layers to leave behind a dense core known as a white dwarf. While the sun may appear as a constant and unchanging presence in our sky, it is a dynamic and evolving star. Its surface is a seething, boiling mass of plasma, with magnetic fields twisting and snapping, creating sunspots, solar flares, and coronal mass ejections. Its surface is a cauldron of activity, with sunspots, solar flares, and coronal mass ejections constantly shaping its magnetic field and influencing the space environment around us. These solar phenomena can have profound effects on space weather, impacting satellite communications, power grids, and even the health of astronauts in space. Understanding the sun's behavior is crucial not only for unraveling the mysteries of stellar evolution, but also for comprehending the delicate balance of our own planet's climate and habitability. Scientists study the sun to predict solar storms, understand climate change, and ensure the safety of our technology and infrastructure. The sun, in all its ordinary yet extraordinary nature, remains a focal point of scientific inquiry and a symbol of the intricate connections that bind our universe together.